Hi, in this lecture we are going to take a look at a set of problems related to curve sketching and see how the principles we talked about are applicable in a given set of problems. So the first one that I'm going to take a look at is the following: y is equal to f of x, that's equal to 8x squared minus x to the power of 4. So the question is to graph this function. What were the issues we studied? We said we have point plotting, domain, range, intercepts, symmetry, asymptotes, and derivative analysis. Let's take a look at the domain of this. What is the domain of this function? Set of acceptable x's. Well, in this problem any x would be acceptable, so the domain is the set of all numbers. For the range we have to wait to see if the other clues that we are going to obtain later on is going to help us figure out what the range is going to be. How about the intercepts? Intercepts of this function, I set x equal to 0. That gives me the y is equal to 0. So when you place x equal to 0 here, y is equal to 0, that tells you you're passing through the origin. Now we turn the table around. I set the y equal to 0. If y is equal to 0, I'll get 8x squared minus x to the power of 4 equal to 0. We might try to factor this. It's going to become x squared times 8 minus x squared equal to 0. Either of these two factors could be 0. Either x squared is equal to 0, which tells me x is one of two numbers. The roots here are double roots, x equal to 0 if you wish to make a listing again. Another roots which is also again 0. The other factor, 8 minus x squared, you set that equal to 0. That tells you x squared is equal to 8, which tells you x is equal to plus or minus square root of 8 or plus or minus 2 square root of 2. So what we have here is a set of x-intercepts. And here of course the y-intercept happens to be same as the x-intercept. Next item to take a look at is the issue of symmetry. So here for the symmetry, we notice that our function is an even function. Degrees of this polynomial are all even. That makes the function to be symmetric with respect to y-axis. So f of minus x is same as f of x. F of minus x, what is that? It's 8 times minus x squared minus x to the power of 4. That's exactly the same as 8x squared minus x to the power of 4. So we have symmetry with respect to y-axis. We don't have any other kind of symmetry in this problem. How about asymptotes and tails? So we want to study the behavior of the function far away from the origin. Well, this problem doesn't have asymptote in the conventional sense. You don't have any division by 0, or you don't have certain trig functions. So none of that shows up here. However, we still need to think about the tails of this function. Domain is the entire set of real numbers. So we need to know far to the right and far to the left what's going to happen. So here I come and ask asymptotes. We said, well, there's none of them. For the tails, we still study when x goes to plus infinity, what happens to y? Let me write the function here again. 8x squared minus x to the power of 4. When x goes to infinity, this function is dominated by its largest power, x to the power of 4. Because of a negative in front of it, this is going to go to negative infinity. When x goes to negative infinity, same thing happens, because we are raising it to power, even power, you get the same answer. This means one tail of the function is in quadrant 4, in the other tail of the function is in quadrant 3. So far our picture has the following information in it. Here's my first tentative attempt at drawing the picture. We have a double x-intercept here. Suppose this is 1 and minus 1. We got the x-intercept 2, radical 2. That is, well, radical 2 is about 1.4. Doubling that gets you 2.8, close to 3 almost. So 1, 2, 3, and we have an x-intercept here. Double x-intercept here, and minus 2, minus 3, again another x-intercept. This location, the fact that at x going to plus infinity, y goes to minus infinity, means the function is has a tail in this location. So here is, if you wish to call it, the right tail. And on the other side also I have, perhaps we are not quite sure how this tail is going to look like, so I just draw a line here, left tail. So presumably we go to, from this left tail, we have to go through our x-intercept. This was a single root, so it's going to cross over. Double root makes us bounce back, and then we have to go through this x-intercept and then go down again. So here's my current guess, that I start from the left tail, have to cross through here because the root was a single root, go here, turn around. This was a double root. A double root you turn around, and then here's another single root. I have to go through that and go join the right tail. So this is, once again, it's our guess. We have to go and collect some other information to make sure that our statements about what happens at these particular x-intercepts is actually correct. Moreover, we need to know, well, where the turning point is going to be. With these points still need to be found out. We at the end we want to go ahead and find out where the inflection points are going to be. Obviously there's going to be some inflection points at these locations if our guess is right. So what do we do next? We have to go to the calculus portion of this problem, which is the derivative analysis. The first, I'll go after the first derivative analysis. First derivative analysis, I need my derivative, of course. First derivative, I go ahead and take a derivative. Let me just remind myself again what the function was. F of x was 8x squared minus x to the power of 4. So its derivative 16x minus 4x cubed. I want to set this thing equal to 0. Find the locations where the derivative is 0. That's the only kind of critical points we have here. There's no point at which derivative would not exist. So that's all I have. So I set this thing equal to 0. I factor 4x, and that's going to give me 4 minus x squared. I go ahead, if you wish, factor this thing one more round. So f prime of x became 4x 2 minus x 2 plus x equal to 0, gives me 3 roots. if I set the first parenthesis equal to 0, I get x equal to 0. Second one gives me x equals 2. Third one gives me x equal to minus 2. These are my critical points. They were all of the variety that make the derivative 0. Excuse me. Next, I go make my table. In my table, I have first line x-axis reserved for x-axis. You remember that I mentioned my tables will have the x-axis running horizontally, and many text, for some reason, x-axis is recorded vertically. So just be aware of that when you are doing comparison. This might be a little bit more friendly. So here I have my f prime. F prime, you have a choice of writing it in this style or just in the compact form. Typically, for what we want to do, this is easier to work with. You don't need a calculator to deal with that one. Perhaps with that you might use a calculator and get yourself into some problems. So here it was 4x times 2 minus x times 2 plus x. That was my f prime. My critical points are minus 2, 0, and 2. So my domain is the entire set of numbers. I go ahead and pick some test points. Here's some test points like minus 3, minus 1, 1, 3. So the green ones are test points. I take a test point, plug it here. Let's see, how do we talk about it? 3. It makes the first parenthesis obviously positive. 4x positive. 2 minus x negative. 2 plus x is positive. So you notice that I just talked about the signs as opposed to going and calculating things. That's why this factored form is convenient to use. So at 3 I got positive. Now, so long as these roots that you have are single roots, that is, they show up just once, your signs are going to flip-flop. You better go ahead and make sure of that. So like if I have 1 and I plug it here, first item positive, 2 minus 1 positive, 2 plus 1 is excuse me, I made a mistake here. Let me go back and correct myself. This was, of course, I mentioned it is negative. So you see the advantage of double checking yourself. I was just going to make a mistake, and by checking another point I caught my my error. So when I plug 1 here, I get positive. I was expecting the sign to switch. I noticed both of them are positive, so something was wrong. I had to go and check it again. If I get the signs wrong, then I'll be in trouble. Let's try minus 1. Minus makes the first parenthesis negative, second one positive, third one positive. So overall we have negative. Minus 3 makes negative, positive, negative. Product of two negatives, I'll have a positive at the end. At these points, these are just where the derivative became 0. So these are crucial points for us. Let's see what we can say about these points. The function f, if it has a positive derivative, it has to be going up. So it's going to be increasing. Negative derivative, it's going to be going down or decreasing. Positive derivative again implies that we are increasing. Negative derivative, we are decreasing again. So let's harvest this problem right now. Let's produce some information about this. Intervals of increase. Let me write this thing further down maybe. Okay, we are increasing here and here. What number do they correspond to? We report our answer based on the x-axis. From minus infinity to minus 2, I write all of my intervals, open intervals. Let's just adopt that notation. From 0 to 2, intervals of decrease, decreasing here from minus 2 to 0, and then again from 2 to infinity. From the first derivative analysis, you also get the information about the relative maximum and minimum. Here you see that you're going up and then going down. So right here we have our relative max, because we went up and then down. And again, well, here is going to have our relative min. And one more time, here's the relative max. So we might go ahead and record the information that relative max happened at plus or minus 2. Since the function is even, I can compress both of them, write it in that way. And one more time, we need to have the equation, original equation was 8x squared minus x to the power of 4. So to find the height, I plug my number here. I'll have 8 times 4, that's going to be 32 minus 16, and that makes a 16 for me. Relative min is here at 0. I plug 0 here, I get 0, 0. So how do we use this information? Let's go back to see what are we doing with our care and guess. We had a guess that we are going up and then down here and up again and down here. Additional information we found was these maximums happen at plus or minus 2. So I have to push it a little bit further to the left. More or less it's supposed to happen here. So I was off by making this curve bend too lazily. It had to come straight up, and then my minimum is at 0 as we were expecting it. So my picture's kind of improving right now to have something looking like this. I'm coming here, turning around at minus 2 and 2, turning up, coming down here, and diving all the way down. So our first guess was kind of right. What other information were we expecting to get? Well, we want information about this point at which the concavity changes. For a while this function is concave down. Let's just shade it so you see, like up to some point here it is, looks like it is concave down, and then it goes into a different kind of a behavior. For example, let's show it by this color. Then it's concave. See. So we need to know this purple region. Where is it that's concave up? To do that, we have to go to the second derivative test. Let's go ahead and perform that. So second derivative test. We had that, you remember so far we had y prime is equal to, that was I guess 16x minus 4x cubed. Is that right? 16x minus 4x cubed. Second derivative becomes 16 minus 12x squared. So I set the second derivative equal to 0. I get x squared is equal to 16 over 12. Simplify that to 4/3. Take square root. I have two roots here. 4/3. You might want to simplify this a bit, depends on your taste. Plus or minus square root of 2/3. That is slightly more than 1. Okay, so 1.3 or something. So let's go ahead and make a table for ourselves. Here's my x-axis. Again, my domain is from minus infinity to plus infinity. I have two numbers to worry about, minus 2 over radical 3 and 2 over radical 3. My derivative y double prime, here you might just leave it as it is as opposed to factoring it, 16 minus 12x squared. Go ahead, pick some test point. 0 is a nice test point. A number larger than 2 over radical 3. You have to either take out your calculator and calculate this thing, or just guess some number larger than that. Well, for sure 10 is larger than that and minus 10 is less than that. I take minus 10 and plug it here. 10 squared is 100. That's going to be minus 1200. For sure I have a negative quantity here, 0. I plug it positive. At plus 10, again I see negative. So what is the information we get about the function f itself? Here it is concave down. Has to be concave up. And here again concave down. As we cross over, we have our inflection points. Here is, we are switching from this sign to that sign at minus 2 radical 3. Same thing happens here. So these are inflection points. Inflection points. Inflection points, so these two show the inflection points. I have x is equal to plus or minus 2 over radical 3. Where did they come from? I need to go back and plug it in my equation. I definitely would have needed x squared. So you remember for both of these things x squared was 4/3. So y of the inflection point would be once again 8x squared minus x to the power of 4. That gives us 8 times 4/3 minus 4/3. Remember this is x squared. If you square it again, that makes us 32/3 minus, this is 16/9. You can see this. And let's take common denominator, 9. 3 times that is 96 minus 16. It looks like I have 80 over 9. So the information that we have right now can be placed back on this curve. This maybe we draw it one more time so that the picture would not be so crowded. Okay, we had a picture that looked kind of like this. So 1, 2, and 3. 1, 2, and 3. We had x-intercepts at 2 radical 2 minus 2 radical 2. We had our turning points were at 2 and minus 2, and the height at the turning point was 16, maximum at 16. So let's go ahead and make sure that fits. That suppose I put this at, say this is 10, so that's going to be 20. 16 will be somewhere around here. Next interesting point was inflection. 2 over radical 3, 2 over radical 3. That is more or less where it says 2 over radical 3. The height was 80 over 9. That is almost 9, a little bit short of that, so that comes almost here. So this was 16 and this was 80 over 9. And we had similar picture on this side, just a mirror image of it sits here. We had 2 tails. We had left tail and the right tail. So this is all the critical information we collected. All we have to do is to connect it by a nice curve. And here is well, my picture didn't turn out as nice as I wished for, but here we turn around and then we go down. I forgot to mention that we of course had the minimum at this point. So these were the important points. Components of our picture are all labeled here. Okay, and that finishes up this problem. Let's see what else we can do for an example now. Okay, the next problem we are going to take a look at is this one. Y is equal to x cubed minus 1 over x cubed plus 1. Okay, let's see what we can get out of this problem. Again, we go through the same list of issues. Here we have the domain which we want to answer and the range. I just remember that in the previous problem I forgot to mention what the range is, so let me just go ahead and correct that. Sorry for this. Range, what's the range of this? We see that the function starts at minus infinity, comes to the height of 16 and then goes down again. So the range of this function is from minus infinity all the way up to 16 inclusive of 16. We had to go all the way to the bottom of the problem to figure out the range. Okay, here let's see if we make sure that we don't forget domain of this problem. Well, this is a rational function, ratio of 2 polynomials. There is a chance that denominator becomes 0, and we have to watch out for that. To investigate that, we intentionally go ahead and set the denominator equal to 0. So if I set x cubed plus 1 equal to 0, the only real root of this equation is just x equal to minus 1. So the domain of this problem is all x's other than that. X other than minus 1 will be fine. This equation has two other roots also, but they are complex roots, so we are not dealing with those here. Range, well, let's wait on that and see what the range is. We go back to the issue of intercepts. What can we say about the intercepts of this function? Okay, with the y-intercept, our job is easy. set x equal to 0. Putting x equal to 0, I get minus 1 over 1. That is y is equal to minus 1. With the x-intercept, I have to set y equal to 0. When I want to set the y equal to 0, y is a fraction. To set it equal to 0, we have to set the numerator equal to 0. That's x cubed minus 1 equal to 0. We solve that. Well, what's the solution? X cubed equals 1. Solution of that, the only real solution of that is x equals to 1. We have other kind of intercepts to worry about. They turn out not to play a role here, but asymptote intercept, we have to, of course, figure out where the asymptotes are before we find out the asymptote intercept. So let's go ahead and wait on that. It's going to turn out that there wouldn't be any. Next issue is symmetry. Does this function have any symmetry? So what do we do? Very basic symmetries are symmetry with respect to y-axis, which requires that the function to be even, f of minus x to be same as f of x. Is that true in this problem? Well, let's go ahead. Instead of x in it, I'm going to put minus x and ask you, if I had minus x cubed minus 1 over minus x cubed plus 1, is that same as what we start with, x cubed minus 1 over x cubed plus 1? Meaning, as I go from left to right, would I have the same height? Well, if you simplify this, you get minus x cubed minus 1 over minus x cubed plus 1. That is the same as this. I didn't write this thing very well, but let me write it here. F of minus x. To compare it against that, we see that they have nothing to do with each other. If you try to manipulate by multiplying by minus, all you get is that both items in the numerator are positive and the denominator becomes like this. So f of minus x is the reciprocal of what you had to begin with. It's an interesting relationship, but it's not the same thing. So are they the same? The answer is no, they are not the same, and we don't have such a symmetry. Well, is this thing a negative of the other one? The other thing to investigate, is it symmetric with respect to origin? Is it the case that f of minus x is minus f of x? Well, this is f of minus x. This is f of x. They are neither equal, nor is it that one of them is the negative of the other one. Is such a relationship valid here? And the answer is no. So the two basic symmetries that we know of don't exist for this function. That doesn't rule out all symmetries, but the two most basic ones aren't there, unfortunately, so we have to work actually harder. Well, let's go to an issue where we are going to get something, and that's the issue of asymptote. Let's first deal with the easy one, vertical asymptotes. For rational function, you said you get the vertical asymptotes easily by setting the denominator equal to 0. Let's go back and make sure here is our function. Double check. Here's our function. If you divide by 0, you cause vertical asymptotes. That happens exactly at the point that you're excluding from your domain. So here is our answer. Vertical asymptotes, we set the denominator equal to 0. It's x cubed plus 1 equal to 0. that tells you x equal to -1 is the vertical asymptote. Issue number 2, horizontal asymptote. Well, that's the issue of a limit. We have to take a limit of x cubed minus 1 over x cubed plus 1 as x goes to either plus or minus infinity. Maybe I deal with it one at a time. Here, x plus infinity. When x becomes a very large number, what happens? Well, if you forgot about limits, just try it out. Let x become larger and larger, see what happens. Like you can take a sequence of numbers like 10, 100, 1,000, unless you are extremely unlucky, that's going to tell you the whole story. So when these numbers, x is going larger and larger, x cubed becomes even larger. This plus or minus 1 next to it will pale in comparison, and all you got is x cubed in the numerator and x cubed in the denominator, and the ratio obviously becomes 1. Now let's see a little bit more into this. As this ratio approaches 1, does it approach it from below or above? We notice that the numerator is a tad below the denominator. Like for example, if x is 10, 10 cubed is 1,000, numerator is not, so let me write it down for you. If x is 10, your fraction becomes 999 over 1001. It's just shy of 1. So I put a little bit minus here to remind myself that as I go to infinity, I am coming to 1 from below. Let's try the same at the other end as well. Limit of x cubed minus 1 over x cubed plus 1 as x goes to minus infinity. Try the same trick again. Let's take x equal to minus 10. This becomes minus 1001. Denominator becomes minus 999. So approximately 1 is a little bit above it. So this is same as previous case. It's 1 but a little bit higher. Now I go ahead and let's put whatever we have so far on a picture and see what we have. Very first issue was we have a point missing from our domain, x equal to minus 1. Let's write that down. So minus 1 is missing from our domain. Next issue that we had was we have two intercepts, y equal to minus 1 and x equal to 1. Y equal to minus 1 and x equal to 1. What else did we discover? No symmetry. We had to wait for asymptote intercepts. We came to asymptotes. Of course, we have an asymptote at x equal to minus 1 here. So let's record that. Essentially need two screens so that you see a graph developing while we are discovering the pieces of it. So here is x equals minus 1, which is a vertical asymptote. I rushed a little bit here. These two limits tell me that I have the same horizontal asymptote on the left and right. Y is equal to 1 is the horizontal asymptote, both left and right. Let's just go ahead and draw that. So I draw here, suppose this is 1. So y equals to 1. That is our horizontal asymptote. What other information do we have here? We know that on the right as I approach my horizontal asymptote, I'm a little bit below it. Okay, x goes to plus infinity. The limit is shy of 1. So one tail is here then. I had extra clue to help me out, figure out it's below here. So I had these 2 points. Chances are quite high that I still stay below. At the other end, when x goes to minus infinity, we discovered that we are a little bit above 1. That means here is piece of the puzzle is sitting here. Well, if we were to make a guess that this function keeps going up here close to its asymptote, and here also it's going to appear from this side of the asymptote and just increase and go up. That is what we see. Now we have to go ahead and actually double check our guess. So here's our guess. Our guess is that the function starts from above this thing and goes up close to this asymptote and reappears from the other end and goes through these 2 intercepts and go up here. There's a piece of this that we can make sure of right now, which is we can make sure that there is actually a tail here and another piece of this, another piece of the tail is here. How can we check that? Well, easy to test. Pick a point near your vertical asymptote. Remember, this was at -1, so you can pick a point here that's going to be like -1.1. Plug it in the equation that you have. Let me write it here. So our function was x cubed minus 1 over x cubed plus 1. Let x to be close to your vertical asymptote. Choose numbers on both sides to test. Minus 1.1. Minus 1.1 cubed becomes minus, you use your calculator, 331 minus 1. Denominator is minus 1331 plus 1. Well, numerator is minus 2.3 almost. Denominator is minus 0.3 almost. We don't need to be very precise here. The ratio is about close to 8 or 7 or something. What does that mean? 8, reasonably large number. At minus 1.1, our number turned out to be 8. 8 will be all the way up here. That tells me the tail of this function is sitting up there as opposed to down here. Similarly, if I go ahead and pick another point here like minus 0.9, plug it in my function, I'm going to get a large negative number, which tells me I'm going to be down here. So far what we know for sure is vertical asymptote here, horizontal asymptote here, 2 intercepts here, 2 tails here, and another 2 tails here. The rest of it we are guessing that this is going to go straight up and this one is going to go straight up. Well, what else could it happen? It could happen that perhaps this wiggles in the middle of the road. Perhaps it goes up and down. How do you know it doesn't go up and down? Well, you need the next issue, which is derivative test, to tell you if anything unusual happens. So calculus is going to help us to make sure that we are not missing any important features, but just taking a leap of faith, simplifying life for ourselves and bypassing perhaps important information. So we are going to go ahead and spend a lot of energy, and let me tell you ahead of time, we are going to come back just confirming our guess that this problem is not that complicated. So here's our function. F of x was x cubed minus 1 over x cubed plus 1. What am I going to do now? I'm going to do first derivative analysis. Sometimes they call it first derivative test. Excuse me. So f prime, derivative of numerator 3x squared times denominator minus derivative of denominator, which is same thing, times numerator over denominator squared. Okay, 3x5 and 3x5 cancel out, and 3x squared minus 3x squared makes a total of 6x squared over x cubed plus 1 squared. Now typically we make a table to talk about this, but sometimes we can bypass all of that effort and just be straightforward about it. I look at this expression, I am squaring the numerator, squaring the denominator, so the derivative is positive whenever it exists. Is there any point it doesn't exist? Well, yes, when x is minus 1, you're dividing by 0, so that's, we knew from the beginning, that's out of the picture. But outside of that, f prime is positive whenever it exists. So what does that tell us? That tells us f is always increasing. We have to be careful what that means, always increasing. Remember, the function was defined into two pieces. One piece up to minus 1 and another piece after minus 1. It is separately increasing here and there. These two portions do not talk to each other. So we have to specify like this: interval of increase, intervals of increase from minus infinity all the way to minus 1, and then from the other side of minus 1 all the way to infinity. So what does that mean? We are increasing. Well, for sure we know we don't have wiggles like this. Why not? Well, if you had such a huge bumps in the road, you will have a decreasing tendency somewhere in it. So we can't have that. So we are not sure that we can just remove that. But there's still another nagging concern that perhaps maybe not a big bump, but maybe just a tiny bump like this. Could there be a tiny bump? The more detailed information you need, the more derivatives you have to take, and the more energy you have to spend to see what else. If there is a bump, it's going to affect the concavity. Right now we see that this function is concave up here and concave down here. If there was a tiny bump like that, it's going to influence that. So let's go ahead, take a second derivative and assure ourselves that this is really a smooth way up. Same story here, and that nothing of any interest is happening in between. Our guess was correct that you could just go straight up. So let's go ahead and get ourselves ready for second derivative test. Or analysis. So what is our first derivative? F prime is 6x squared over x cubed plus 1 squared. We need to differentiate this one more round. I'd given you a formula for simplifying life with these cases, but most likely you don't remember that. So we go ahead from scratch and try to differentiate this. Double prime, derivative of numerator times denominator minus numerator times derivative of denominator. 2 comes up front. Derivative of the base is 3x squared, and exponent comes down from 2 to 1. So make sure you double check this thing. Now denominator has to be squared. was squared before, squaring one more round makes it a 4 here. Let's make sure we see this subtraction here. Well, that became kind of messy. Let's see if we can clean it up. From numerator, of course, I have that factor, so I write it out. X cubed plus 1 factors out. Surely I have a 12. Surely I have an x. Let's see what else is left. From the numerator, 12x times one of these parentheses is taken out, and we are left with x cubed plus 1. From the second piece, okay, 12x, we factor 12x. 2 times 6 is 12. X, 1x is taken out. 1x is still here, and 2 of them here, so it makes a total of 3x cubed. Did we get that right? So we had 6 times 6, that is 36. We had to get 12 out, so we are left with a 3. There was x to the power of 4 here, and I've taken x out, so that makes it just 3x cubed. Okay, I guess that's right. X cubed plus 1 to the power of 4 in the denominator. Now let's go ahead and clean this up. I have second derivative is equal to one of these factors cancels one of these, so in the denominator we are just left with 3 of these, x cubed plus 1 cubed. Here I have 12x, and over there I'm left with 1 minus 2x cubed. Now we want to do second derivative testing or analysis. Here I have several factors. I set each of these factors equal to 0 and collect all solutions for them. Either 12x is equal to 0, which tells me x is equal to 0, or 1 minus 2x cubed equal to 0, which tells me x cubed is equal to a half, which tells me x is an unfriendly number, x cube root of 1/2. Or here we have to set the denominator equal to 0 also, and that tells us x cubed is equal to minus 1, which tells us x is equal to minus 1. So to do a sign testing of an expression, we just factor it as far as it goes, both numerator and denominator, find the roots of everything in numerator and denominator, and we make our table. So let me see, I probably don't have much room to write the derivative here, so I just write x-axis. Here I just write f double prime, we have it in view up here, and then I go ahead and write down my numbers. Here I start at minus 1, and then there is a 0, and there's cube root of 1/2, and then of course from minus infinity to plus infinity we are traveling all the way through. We remember that minus 1 is not in the domain. And now for the test point, I go ahead pick some test numbers. So minus 2, for example, minus 1/2, cube root of 1/2. That's going to be rather problematic, but you just go ahead and check that the 1/2 actually fits in this interval. 1 is a good test point here, so you probably need your calculator. All of these roots that we obtained here are single roots, so we expect the sign to alternate. Let's go ahead and check. I put a 1 in this, positive, negative, positive. So sign here is positive. How about 1/2? Obviously here is positive, here is one positive. 1/2 cubed makes 1/8 times 2 is a quarter. And let me see, I made a mistake again. Let me go ahead and correct myself. Start from scratch again. 1, I plug it here, makes positive. When I plug here, of course, I get negative. How did I catch my mistake? Because I saw again another positive, and two positives next to each other is a suspicious thing. It only happens if your root is double. My root was single. I just had one root of this type. So I expect the sign to flip. Here I expect to get positive. Let's try it again. 1/2. This and that are both positive. In this one, you just said 1 minus 2 times an eighth is in fact positive. At negative, this will be negative. This is positive. That is positive. So overall, I get negative here. At and -2, negative, and positive. Is that right? So I get a positive number here. So our guess is right that the signs have to alternate. Our verdict about F is that it is concave up, down, up, and down. We discovered something quite interesting now, that our picture that we drew is actually incorrect. We have an inflection point here and here. We have two inflection points. Our picture was not showing that, so that is something to write home about. Here is we have an inflection point. F changed its concavity from down to up. So here is an inflection. Our picture was not showing that at all. And also this one, this is another inflection point. How come this one is not an inflection point? Can you pause for a moment and think about it and come back? So why is it that it's not an inflection point? Remember, this is not in domain. That's where the function breaks apart. So it can't be called anything, a max, min, or inflection. It just, the function isn't even defined there. So we have an inflection point at x equal to 0. If you plug in your function, you get -1. And 1/2, well, plugging it in the function would not be hard because you're cubing this thing. You get 1/2 minus 1 or 1/2 plus 1, which if you simplify, you get -1/3. So this is the point with cube root of 1/2. And if you take this, plug it in the function, you remember the function was x cubed minus 1 over x cubed plus 1. Well, cube of this is 1/2. 1/2 minus 1 over 1/2 plus 1. That just boils down to -1/3. So what was it that you were going to write home about? What we discovered is that this picture, as innocently interesting as it looked, is incorrect. Here we have an inflection point. It has, the function has to change its inflection. So let's use a different color here to announce that. What's good? Say black. At this point, the function, let's just remember, before 0 it was concave down. After that it becomes concave up. So up to here it was right, it's concave down. At this point it twists the other way. So there is in fact some little bit of a bump, or if you wish, a pothole in this road. It comes down. Then at cube root of 1/2, the inflection changes again, and the rest of our story will be correct, that this thing just stays with concavity down. So there is just this little sink over there. Let's clarify that from this point to somewhere around here. This was the point with the coordinate 0, -1. This one with the coordinate cube root of 1/2, and the height of it was -1/3, I guess. Yes. Over there, the function has a dip. There was nothing there, so nothing to write home about over there. But here, this is what discovered, and there would have been no way, absolutely no way of saying that without going all the way down to the second derivative analysis and bringing that news back. So that completes our problem here. Let me see, did we answer everything? Let's go back. There was an issue here of range, which we left out. Yes. Well, what is the range in this function? If you look at this graph, there was one thing we did not check, which is, does this function ever cut through its asymptote? For example, is it possible for it to behave like this kind of a strange behavior, like go up, come back down, and go there? For several reasons we know that that is not going to happen. One of it is that if it went to go up and come down, it would be decreasing on this interval. We don't have any place where this function is decreasing. That doesn't happen. Similarly, it cannot sink in, go up, and come down again for a fact that it's not going to be decreasing anywhere, and also we don't have any turning points. There would be another style of figuring out that these asymptote intercepts do not happen, but for now perhaps we don't want to make the problem any more crowded than it is. So these are impossible events. So that being said, it becomes clear that the range of this function is all numbers above 1 and just below 1. Both of them are part of the range of this function. Let me color it perhaps. All of these y's are arrived at. Or in other words, if you take the function and just crush it on the y-axis, what's going to be left out of it? Imagine Godzilla stepped on it, and from both sides it just crushed it. And the one section is here, and another section is down here. Everything gets covered except this. So the range is all y's other than 1. We write that range everything other than 1 gets to be covered. Okay, that completes this problem. You notice how long it took to get to the bottom of it, and that is what to be expected. You go ahead and try some other problems, and good luck and God bless.